in the SRG, and she's been here for a couple of years, I guess. Her interest is in operating systems, security, virtualization, and trustworthy computing. And in particular, her work is centered around building systems to provide applications with strong isolation and fine-grained compartmentalization mechanisms. She's done several research internships at Microsoft Research Redmond and Cambridge, and received her MS degree from Indiana University, Bloomington. And Zara, the floor is yours. Go for it.
Thanks, Kasha, for introducing, and thanks everyone for attending. So I'm going to talk about our recent work on Enclave-Aware compartmentalization and secure sharing. So as you probably know, we have a long history of isolation, and since this talk is about compartmentalization, I'm going to start with a brief history of the current state of isolation in conventional operating systems. It's the main job of operating system to provide a secure shared environment of processes, protecting applications from each other. That's why of isolation, that process is there to provide in separate address spaces. And we have other mechanisms like access controls, such as SE-Linux, AppArmor, and features like systems called filtering, such as seccomp, and capability-based isolation. So this is a long history. A combination of these techniques are actually widely being used in existing complex applications. For example, in browsers, in Chromium or Firefox, they use their sandboxes are designed to put untrusted libraries or a part of their code that is actually less reliable, less stable, such as GPU driver or renderer inside processes with limited access to network stack, for example, using seccomp, or processes that cannot, for example, access file systems as much as for the master process, the main process can have. And there is a huge IPC systems here, mostly using pipes for communicating with, between these components. They also may use access control mechanisms like SE-Linux. And as you probably know, SE-Linux is a kernel security module that's designed for user applications to define their security policies on kernel objects, files, inodes, pipes, and sockets. And internally, inside the kernel, it's a complex stack. It has about 200 security hooks that are propagated between all layers of abstraction in the kernel. But in the user space also, this complexity is not handled well. So in the user space, they just let developers to have a static and a very coarse-grained way of defining their security policies and restrictions over the system resources. And that's why in last Microsoft Summit, they were discussing about mostly search questions about SE-Linux was how to disable it, because it's really inflexible and it's hard for developer to define the right granularity of isolation. So the current state of isolation in or conventional operating system is not great. It only allows coarse-grained compartmentalization. We see lots of sandbox escapes. These are only a few of recent ones that I listed here. But as you see, we have container escapes, SE-Linux, AppArmor, namespaces escapes. And especially if the attacker gained the root access, then all our security mechanisms can be bypassed. And there are also a lot of in-process threats that are kind of ignored because so the unit of isolation in the operating system is process. And though we have process-based sandboxes, but it's at the end, it's going to be too expensive for a complex application to put every single untrusted library to a separate process So at the end, we're going to end up with some a process that at least have few untrusted third-party libraries. And when one of these libraries are compromised, then that component is compromised, and we're going to eventually lose our hierarchy of trust in the application. And we also see that, so all of our security that also depends on the operating system, we also see that the operating system itself is getting more and more complicated. We're adding more hardware feature, more interesting feature, but at the same time, we're also adding more vulnerabilities. So there is no sign of reducing vulnerabilities in the Linux kernel. That's why there's the concept of enclaves, or trusted execution environments, that almost all major hardware vendors introducing a form of TE or enclave. Like ARM has TrustZone, Intel has SGX, AMD Save recently for their virtual machines, and RISC-V has Keystone, that is more research project than really supported by some big team. But so the concept of enclaves are, so the implementation of enclaves is different. For example, SGX has defined enclaves as a user space protected area of memory, encrypted, and it's any code inside the enclave, even the runtime of the enclave or the minimal kernel that is there, is protected from the OS or hypervisor that's running in the privilege mode. And TrustZone implementation is different. It's not depends on memory encryption, but it's depends on it's implemented as a virtual core of a physical core. So a secure world of TrustZone can have a user space privilege ring, EL0, the same as the normal world, and kernel level of privilege, EL1. And the two world, normal world and secure world, can only communicate through SMC calls to secure monitor mode. That's the highest privilege mode of in TrustZone in the ARM architecture, EL3. So TrustZone allows not just partitioning the memory, SRAM and DRAM, also partitioning peripherals and interrupts. So it's the whole hardware architecture that can be divided to secure or non-secure one. That's not the case in SGX. But at the high level architecture is really similar. You have your in-enclave kernel and user space processes. That's for example, in TrustZone. Enclaves are user space processes that are communicating with their kernel system calls, exactly similar to the architecture we have in our normal board. So they expected enclaves to be really small. So these kernels that are designed for they're actually these different vendors, and they are completely independent and not aware of their security model of each other. So that's why the recommendation for an ideal enclave is keep the enclave small, minimal interaction with outside world, and it would be great if it can be verifiable as well. But in practice, after several years of enclave programming, and we see lots of in enclave enabled application, in practice, there is no perfect enclave. Enclaves are used in very complex applications in web services such as Tor, HTTPD, and they used as a secure reference monitor, for example, for implementing access control mechanisms of application in an isolated environment. They used for secure databases, lots of privacy preserving machine learning and data analytics for from Hadoop, from ML darknet frameworks, from TensorFlow, and we see also in enclave programming in edge devices. For example, ARM distributed data sharing library for example, secure connection and data sharing between autonomous vehicles and medical devices. So in all of these use cases, there are lots of dependency to the underlying operating system resources, in both kernels actually. And this is for their design. For example, if the design is multi-threaded, or if they need to communication with other enclaves or with other applications. So there's an IPC or RPC communication involved, or if they actually need any other system resources for networking or file system as a storage. So as we expected, this semantic gap, this lack of knowledge between the two kernels that are involved, caused lots of attacks, lots of very practical attacks on enclaves. Almost all TE systems could have the similar vulnerabilities that are basically all of these attacks are because of insecure interactions of enclaves and host applications with systems resources, with kernel objects. For example, coin attacks last SPLS, they introduced I think more than 80 vulnerabilities in all major TE enabled systems like Google Silo, Open Enclave, and the Enclave SDKs. And the attacks were about how a malicious host application can launch malicious threads and use vulnerabilities such as time of check, time of use attack-based attacks, nested calls, out-of-order calls, and at the end could gain the full control of the enclave and could extract secrets such as remote attestation keys and other secrets from the enclave. In this paper, they mentioned that this is a deeper problem than we solve with API synthesizing. It's really more logical threats and lack of enough privilege separation between the components in enclave. And there is no defense in depth mechanism in TE systems to at least avoid propagation of vulnerabilities, or let developers to plan for what happens if the enclave is compromised. So as another example, on trust zone enclaves, we have boomerang attacks that actually use the insecure shared memory and RPC communication between the normal world and trusted application in the user space of secure world. And compromise the malicious application could trick the trusted application, and through crafting the system calls, it lets the secure operating system to make the normal operating system, the Linux, accessible, the memory be writable and accessible to the normal world. So this is a full system compromise. And the main reason is the insecure share memory and insecure access control and lack of privilege separation between the two worlds. And since the secure world in trust zone is more powerful than normal world, it can access actually the normal world resources. So this can have more damage than, for example, compromising SGX enclaves. Another set of attacks, horizontal privilege escalation in last using security, shows the similar attack surface, but this time a compromised application can compromise another application that's using the same setup, for example, enclaves. So with looking at these attacks, and at the end of all of this paper, it mentions that this is deeper than API synthesization. That's the actually only security mechanisms that major TE systems have. They say, okay, we have this interface, and only checking input and output of the interface should be enough. But we see this is a semantic gap, and going deeper to look at these attacks, we find out the main problem is the data flows in TE-enabled application is really complex. The data flows in a simple application was already complex, and now we have a new set of stacks in another privilege layer, and the data flows is getting even more complex. It's communicating inside the host application, especially multi-threaded applications. It's in the shared memory. It's communication of both worlds with the systems objects, and communication with other, for example, threads or processes in both worlds. So going deeper to find actually the root cause of like these vulnerabilities and how we can actually protect it, the system from that. We analyzed 41 T-enabled application in addition to previous vulnerabilities, and categorized the vulnerabilities to 3 classes. The attacks are because of insecure threading or procedure calls, or because of memory vulnerabilities that can be in shared memory or memory vulnerabilities in each world in Enclave or the host application, or it can be because of insufficient privilege separation, again in both worlds. And we actually identified 6 major kernel objects that are directly targeted in these vulnerabilities, or misuse of these objects could increase the damage. For example, they could propagate the vulnerabilities, or they could transfer or the extracted secrets to untrusted source. And these objects that we identified are threads in both world address spaces, files, sockets, IPC or RPC pipes, and the RPC between the 2 worlds. And between the application we analyzed, only 4 of them actually didn't use at least 3 of these 6 kernel objects. So these are heavily used in T-enabled applications. And as you see, most of the applications actually are vulnerable to at least 2 of these class of vulnerabilities. And existing TE systems actually not targeting any of these vulnerability classes. The popular one that is in Enclave library operating systems, for example, SGX LKL, the main focus is porting the entire application inside an enclave. So, for example, SGX LKL has a large portion of Linux kernel inside an enclave, and they can port unmodified application in the enclave. But at the end, it has a very large TCP, and it's not practical for complex application. But the large TCP itself then requires in enclave compartmentalization. So there are several words, such as I think Enclave DOM, and for in enclave compartmentalization and providing more isolation inside the enclave. And they don't have don't consider malware enclave. What will happen if the enclave itself is compromised and wants to like attack, like can attack the host application, or send the secrets to outside world. And then there are other form of like TE systems, partitioning frameworks such as Google Silo or Microsoft Open Enclave, and they're also similar, only they're doing input-output synthesization. CVET, that is a Java partitioning framework, is actually doing a bit better. It's doing dynamic taint ranking on enclave objects, but only focuses on the interface, not the kernel objects. And Enclave Sandbox framework, that is SGX jailed, it only targets malware enclave and protecting application if the enclave is compromised. So that's why we started to think about how to solve this problem in a principled approach. And we built Sirius. It's the first TE compartmentalization framework that is operating in both worlds, and enables mutually distrustful compartments in Enclave and in the host application, and in the shared environment between them. Sirius depends on decentralized information flow control for avoiding information leak. And it's at the end, we really wanted to Sirius be lightweight, to be able to have enable it in small devices like edge devices, mobile devices. And we also targeted trust zone enclaves for the first prototype, because as we showed, trust zone attacks can be more critical since the secure board has the full access to the normal board, and the attacks can damage more. So in threat or threat model, it's really important to note that we're not violating the original threat model of enclaves here. Still, even we provide the compartmentalization inside an enclave, still the compartments are part of the enclave. They are protected from the operating system and user space attacks, small one. But none of TE systems actually covering the wide range of attacks that we're considering here, such as compromised host application or misbehaving enclave or any of insecure interactions of threads running in both worlds with other threads, with through concurrent calls, shared memory, or other system resources. And they're not considering providing a mechanism for defining multiple security layers, defense layers for protecting kernel objects and for protecting the data. So we picked diffC instead of classic information flow control because this TE-enabled application, TE design is not centralized. It's at least 2 kernels are involved, and extending a central model, for example, extending SE-Linux or like a combination of techniques in normal world operating system was not really reasonable for what we wanted to design, to consider all the and all complex flow of data in both worlds. So diffC allows every security principal to define their security policies. And these security principles can be threads, can be processes, so different granularity of entities. For example, we have diffC systems in programming languages, especially like GIF, CamFlow, and we have previous diffC operating systems, the Fulum or HighStar, for example. Fulum is a little bit so Fulum implementation of diffC is in the user space mostly, in file descriptor abstraction layer. And since it doesn't have the communication with the kernel, it's introducing a very large overhead of constant communication between the user space and kernel. HighStar, on the other hand, introducing the custom designed from scratch diffC kernel, but it's non-POSIX kernel, and it's that's why most of this diffC operating system just remain the research project. So we really wanted to find the right abstraction, both inside the kernels and or introduce new abstraction to make this more practical. As a really simple brief background on diffC, or labeling models is actually it's based on tags, unique tags that every object can have a tag. Labels are just set of tags and integrity is vice versa if the integrity label of beta is a subset of integrity label of alpha. And this simple rule works for any object. And for every tag, we have 2 capabilities, T plus and T minus, that are representing privileges. Every tag owner can pass these capabilities to another thread, And if a thread can have a T plus capability, it can add that tag to a label. And if it has a T minus capability, it can remove the tag. So there are safe operations, such as adding a tag to a secrecy label, or removing a tag from integrity label. But there are unsafe operations, such as declassification, that you're removing a tag from secrecy label, or endorsement. You're adding a tag to integrity label. So unsafe operations should only be done by the owner or the authority. That the authority can be granted or revoked by the owner. So how this Sirius is actually working? So Sirius is a compartmentalization framework. And since we're targeting major kernel objects, we wanted to pick complex applications that actually we could show how the compartmentalization works. So we picked Apache HTTPD, Darknet in Enclave Darknet machine learning framework, and the distributed data distribution from the ARM libdds. So, for example, if you're considering the Apache HTTPD, there are the compartmentalization of OpenSSL for having a secure part of the OpenSSL that's doing crypto operations inside the enclave, an untrusted part that is communicating with the application, the HTTPD web server. And then there are lots of communication. It's a multi-threaded environment. There are lots of communication with outside world, with untrusted, for example, resources such as files, or there is enclave resources such as the driver, the dev TE that's communicating with the enclave driver, the file secure storage. And all of these layers should be protected. All of these layers should be, so the developer should be able to define the security policies for that. So we show how we compartmentalize all of these applications, and how it's actually providing a very efficient way of doing that. Sirius API is small. It's really, we wanted to make it sure that it's not that complex, because traditionally diffc and all kind of information flow control systems were hard for developers to work with, hard to program the security policies. That's why we wanted to hide the details as much as we can. And as you see, for example, the enclave operations are kind of the same operations from the user perspective. You create an enclave, you have eCall, OCall for calling procedure calls, and you can delete the enclave. For defining security policy and labeling, we actually only have a few calls for passing the capabilities and granting authorities, grant or revoke of authorities, disabling or enabling access to an object, and creating sklearn for creating a labeled thread. And for creating labeled object, actually, we try to extend the existing syscalls, for example, open, socket, or pipe, to create labeled object instead of introducing new system calls. And for address space objects in both worlds, we had to introduce a new address space abstraction called IMC, isolated memory compartments, because the unit of isolation in operating system is processes, and we needed finer grain in process compartmentalization. So we introduced a new abstraction layer into the virtual memory rail of both kernels called IMC. And IMCs actually have really few APIs. You create an IMC, you have memory management operations such as malloc, free, memprotect, memmap to manage memory inside an IMC, and at the end you can kill the IMC. So as a brief overview on Sirius Enclave lifecycle, it's the process of creating Enclave is similar from the user perspective. It's like just calling screate Enclave, but inside the kernel, only that calling thread will be labeled with the kernel security module of Sirius will create a unique for that thread, add it to its secrecy label, and then pass the request to the secure kernel. The first place is secure monitor. The secure kernel then creates additional tag for the enclave thread and add it to its to secrecy label. D here is the dual permission. It's, when a thread has the dual permission, both T plus and T minus capabilities, then they have full control over that tag. And after adding both tags to the secrecy labels after the threads, only that two threads can communicate with each other. And as you see, no other thread no other thread with having the right label can communicate with any of these authorized one. And both kernels are going to kill the violating thread. So Sirius, for address space compartmentalization, we have the new abstractions that's dividing the same process virtual memory address to separate IMCs. And each IMC is backed by a virtual page table for every thread. And for IMC operation is like still it's a labeled object. So if an IMC owner has the T plus capability, it can only do the default operations that the owner assigned for the IMC. For example, if the owner of IMC, the creator of IMC, assigned the permission of read and write, the other thread that has the T plus capability can only do that operation. For example, it cannot execute the code inside that IMC or send the content of IMC, for example, via memcopy. And if a thread has also T minus capability, then it can change the memory layout of IMC as well via IMC memmap, adding or removing page to the IMC, or for example, send the content to outside world. So as an example, here you can see like we can define now shared IMCs for like communicating between different threads in both folds. That this shared IMC can have both enclave or normal world owner. For example, for the first one, the M1 IMC, the enclave thread is the owner. So the normal world thread can only do the default operations on that M1 and not any other operation. For the M2, for the M2, the enclave thread does not have any capability. It's not in the secrecy list, so it cannot access to that memory. But we can give that, so we can use this partition memory for example, if the host application has another like secret that it wants to protect from the enclave. This is like a simple example of how the IMCs are used in a single thread. IMCs actually can have both hardware and software backend. We show how we optimize the IMC with the hardware memory domains. So because like fortunately in most platforms we have a feature of like a hardware feature for memory safety. For example, Intel MPK or like tagged memory. So we wanted to design IMCs in a way that it could be backed by the hardware as well. But the default version is just the kernel backed with virtual page tables we introduced. So a thread can create IMC and then grant permission to that. For example, here read and write, and then it can call IMC malloc, pass the IMC ID, and or make it accessible or disable the access if it's doing some untrusted computation, and at the end free the memory blocks. For multi-threading is the similar process, only, for example, they can add a same virtual memory via IMC map to different IMCs. So different IMCs would have the separate view of the same virtual memory. And then the parents can create like 2 threads with S-clone with different view of the same IMC, and by passing the IMC IDs and the data structure to the clone. So the address space abstraction actually was like not that expensive. It's only 2,000 line of code is changed in the Linux, and around 500 in the Trustzone operating system. And we provide like a familiar memory management API. For the hardware backend, we use our memory domains. That's memory domains are like 16 domains. That's you can see like 4 bits of first level descriptor in the page table address translation. And these 16 domains, they have a specific register, DAR, that's it allows to change the permission of these domains. For example, make it no access or like full access, and without going through the TLB and to the address space translation. So without any TLB flush, you can change the permissions. That's why we see like about 48 improvement for like IMC map and 38% of improvement in the trading cost. So it's a little bit limited because it's only providing 16 domains. But if your application doesn't need more than this number of like compartments, it's a very like more efficient way of doing using IMCs. So you can call IMC create hardware backend. So for other kernel objects, because we also covering like files, sockets, and pipes. For other kernel objects, we changed the VFS layer of the Linux kernel a little bit. But the main implementation part was designed from scratch security modules in both worlds. Like these security modules are implementing a set of one set of clean rules of DeepC that are used for then if you at the end of this having these security hooks, for example, only we have 15 security hooks. So you can use these hooks for any kernel object. So that's actually a good way of implementing a full system isolation, but with minimal security module like implementation, because the information flow control rules are one set of rules, but you can like add extend it with, if you have additional, for example, kernel object, you just like use the same security hooks for that. That's why we only have 15 hooks. That is really not comparable with, for example, ST Linux or AppArmor with like 200 security hooks. And the total implementations in both worlds was about like 15,000 lines of code. But compared to, like, for example, the other centralized way of like access control mechanism, it's order of magnitude less lines of code. We evaluated our Sirius by changing Opti. Opti is a Trustzone open source Trustzone TE system that's like widely used in lots of applications. It's, I think, the only open source one for Trustzone that is kind of complete. And show that Sirius not only is adding overhead, is actually improving its performance a little bit, because we are removing layers of security checks in every abstraction layer. with this unified access control and in bold. So we don't need to have input output checking or object checking in every layers. We're just replacing that with Sirius hooks. And the cost of Sirius threads with S-clone or with hardware S-clone is very near to pthread, and because it's implemented as an extension of clone syscall, and order of magnitude better than fork and process-based isolation. The other thing about the S is that here we don't share everything by default for any thread. In opposite to fork, that is everything is shared and it's hard to reason about the security of child. Here, the parents can make sure that the child doesn't have access to all the resources all the labeled resources. For memory cost, we replaced, for example, the OPTI shared memory with the IMC-based shared memory, and we showed Sirius IMC is improving the OPTI with 16%. And there is an OPTI CSR. It's a research project for providing a pointer verification based for protecting boomerang attacks. And we also outperforming that. And instead of checking every pointer, which the Sirius compartment address space isolation is improving the performance and protecting the environment as well. And for mProtect, if the IMC for the hardware-based mProtect, if the permission change is one of the DACR permissions, we're doing about 1.14 times improvement. But if not, it would be the same as IMC mProtect, the same as mProtect. For overall, when the Sirius is enabled in all file systems and all the networking stack, with the LM bench macro benchmarks that shows between 8 to 20% overhead, and compared to OPTI secure storage that is encrypted, and it's very small and only can be used for some encrypt for example attestation keys. It's about 80 times more efficient, better performance. If you, for example, don't need that much encrypted environment, but you still want to the files be only owned by the enclave thread, not by the normal world. So for or compartmentalized HTTPD, we see about 10% in average overhead. But we're Sirius shows that how we can have a compartmentalized environment that, for example, OpenSSL is only 2,000 lines of code of the crypto part is inside the enclave, and instead of having the whole, it's about 500,000 lines of code. It's a large library instead of putting the entire one inside into the enclave. And we provide a protected way to communicating between the OpenSSL enclave and a storage enclave, because they don't need to have the right to have the same access to, for example, file systems or communicating with other threads. For example, in the HTTP web server, only the enclave, the threads that are communicating with the enclave are are authorized for accessing the shared memory, and other threads cannot do that. And some other details of the compartmentalization that I'm not going to go through that. The same for the Darknet framework. It's a threaded environment, and we protect models from the. So this is this design is for porting enclave models inside the trust zone to avoid membership inference attacks. but that design is still needs compartmentalization because it's a multi-thread complex application, and there are lots of communication with the file system for protecting models, for communicating with two worlds, and we compartmentalize that. But the darknet TZ itself already inside the trust zone. We just add additional layers of defense on that. And the same for ARM-lib DDSSEC, that is already on the GitHub is already available from the ARM. We just had additional compartmentalization for all layers of interactions with the systems of the both worlds. So for future work, we actually ported a part of, especially the IMC and memory isolation was useful for secure, for provide secure bindings in programming languages. So in my recent work with Verona team in Microsoft Research, Verona is the memory safe language that provides concurrent ownership, and it's actually trying to be a better model for pervasive compartmentalization, and it has lots of concepts of Rust, but they want to have a more secure interactions with the outside world. So there is no unsafe bindings in Verona. And one of the things we did was improve the IMC concept for sandboxing Verona unsafe code, any communication with the C, C++ code, and every region of Verona. So Verona is a region-based programming language, so every region can have different memory management. And now we're designing the system that every region would have a different sandboxing mechanism, would be IMC-based, WebAssembly-based, or other hardware features. For example, cherry or tag memory for making sure that developers can define a perfect balance between security and performance of their system. And other future work is we're currently working on improving the work for Intel architecture and SGX support, and continuing working with the Verona team to complete the sandbox region abstractions. And we're also, there's a concept of co-process abstractions in Cherry BSD that is really related to what we are doing, and we are really interested to see if we can compare or work with that as well. That's my talk, and I'm happy to take any question. Thank you.
Thank you so much, Zara, for a very interesting talk. If anybody has questions, please feel free to unmute yourself. If you don't want to ask a question by audio, just put it in the chat and I'll read it out. Thank you. Okay, while we're waiting for questions, Zara, so I was, from what you're saying, it looks like you actually need to rewrite the applications because, for example, in the HTTPD example, you had to actually, or Apache example, you had to rewrite that application in order to use Sirius. So does that mean that all app developers will need to rewrite all the applications in order to get safety?
That's true. You need to provide the application, but we actually implemented the APIs in a way that be really easy to define the security policies. For example, if you want to create a labeled file, you just have the same open system calls with passing, for example, slabel flag, so it will create a label file for you. So the enclave calls, for example, for opti is the same. You create an enclave, you have the eCall, OCalls, but internally these diffs principles are implemented inside the abstraction. So we actually didn't have to change much of the code. Like for example, HTTPD, it was like about 2000, but both for the OpenSSL separation and the HTTP changes. But for example, for darknet framework, it was less than like 500 or about like 400 lines of code change that are mostly adding the like APIs. It's not like modifying a lot of like the code, or legacy code base.
No, I understand that the modifications are straightforward and almost routine because you're going to tag everything. But if you had a system where some applications were modified and some were not modified, some were the application developer didn't want to modify them, how does that affect the security of the overall system?
So if you have, for example, using an untrusted library that you can't modify that, but it's going to be linked. That's why we have the IMC concept. So you have the loader, and you have you can load that library to a separate IMC, and like restricted access or label your resources. Basically, for example, you have like this secret part of the memory and files, and if you load that to other compartments, that should be enough. So you don't need to like know.
Right. No, I think you talk about isolating subcomponents such as such as an untrusted library. But let's say that you have SSHD and HTTPD running, and OpenSSH decides they're not going to use Sirius, but HTTPD agrees to do it. Right. So you have a system of server running with both trusted or rewritten and not rewritten legacy components. How does it affect the overall security of the system? Would it be the case that the SSHD is now open to attack, even though HTTPD is not open to attack?
So if your HTTPD components that you care about, like your, for example, keys, if you label them, their flow should be secured. It doesn't matter if the other applications that are communicating with are not using Sirius. So that's why for the developer of like that application, is only important to like pick their own secrets and label them, and that's enough. Like if the other applications that they're communicating with, they need to like access that secret, they need to ask for permission. They need to passing the capabilities. So as long as they don't have it, that should be fine.
Okay, thank you. Are there any other questions?
Hello there. Hi. I'd like to ask a question if possible, please. Hi. If I'm understanding correctly, one of the key points about this is that the communication channels that are established, the labeling is maintained throughout the kernel and is associated with the kernel objects appropriately.
Yes.
Yes. Thank you very much. That's much appreciated. The other question is, are you familiar with Google's Project Oak?
Project Oak, the one that is secure data sharing?
It used to be along those lines, but I believe you might be of interest in that area because it's very similar.
Actually, Mort introduced me a few days ago. I haven't looked at its details, but it can be related. I haven't seen any previous separation in that space from like communication.
Sorry. Yes, it definitely is orthogonal to this, but is it could be very much of interest. Thank you very much indeed.
Yeah. Thank you. Yeah, I should look at that too.
Yeah, it's important to note that Oak is very complementary to this, but the key contribution of this is also the diffc model, where you can have multiple enclaves, and the API naturally separates the concerns, whereas Oak is more concerned with the low-level details of encrypting enclaves and data at rest and moving between them. So it should be possible to build like an Oak backend using Sirius. But the Sirius programming APIs are much more ambitious, I think, than Oak.
Yes, I think we're thinking along similar lines here. That's very interesting. Thank you very much.
Yeah, I actually wanted to be in a low level enough, because most of these data flows at the end are going to be between this kernel object. So now it can be used, for example, in the Verona use case, we're using it for language-based compartmentalization, or for example, for other T-enabled applications like Oak. So it's low level enough that now we are experiencing with applications and user space use cases to improve their work. But yeah, it's a little bit low level.
Any other questions? Okay, well, we are also running out of time, so let's thank Zara. I'll thank on behalf of everybody else who's muted. Thank you so much for a very interesting talk, and we will continue with our seminar series next week. I hope you will have a chance to join us. Look forward to seeing you next week. Thank you. Bye-bye.
Thank you very much.
Zara. Wonderful.
Bye. Thanks.
Bye-bye.
Thank you very much indeed.
Thank you.